Okay, hi guys. So my name's Chris. I've been doing LabVIEW for 20-something years. I don't know, 10% of the people here. It's nice to see some faces after a while, but yeah, good also just to get a number of like-minded people in the room. So I hope you all pick something up out of this. I'm just going to talk, but feel free to ask questions and just jump in if you feel like it. We can have a bit of time at the end, but it's often easier just to interrupt. So all good if you want to jump in. Yeah, so this is about some cool ways to get more out of your code. If you need to do things a bit faster, we've all had applications that run and they're not fast enough at different times. So we're going to go through some of the main ways that you can speed your code up. We'll talk a little bit about why you want to do that. Profiling is very important because unless you've got a way to measure how fast your code's running, you can't really effectively speed it up. And then we're going to do a lot of demos. There's an optimization chapter, so there'll be code. Okay, so thanks Nick before for kind of setting us up here. This is about writing faster code, which, as I mentioned, starts with profiling. Then you can optimize, and you have to then see if what you've done hasn't broken anything and whether it actually makes a difference. So that's the basic workflow for getting your code to run faster. I'm not at all going to talk about writing your code faster, like quick drop. And in fact, the point here to make is that making your code run fast is maybe a little bit anti-quick drop in some ways. So when you're really banging code out and you're struggling to meet a deadline or whatever it is, you're not going to write the most efficient, optimal code that you can. So sometimes you need to just step back and take your time and think about the best way to approach a problem. And that's a bit the vibe here. So we're going to limit the talk to pure LabVIEW. So no add-ons and packages and libraries and external code. There'll be a bunch of demos. So mainly I'm going to compare some low-level functions, look at things that we commonly use and some alternatives that are in the palettes and maybe some third-party VIs that are also similar and easy and fast. So what I do and what I measure, I've tested a bunch of my code on a few different machines. And I found with my demos that some of them you see one function is a lot faster than another. And on a different PC, maybe it's like got many more cores or much more cache or something else is different. You'll find that a different VI turns out to be faster. So whatever you do when you're optimizing, you have to test it on more than one machine and preferably test it on the machine you intend to deploy to. That would be the best way. But nevertheless, you can usually draw pretty good conclusions from a single machine. So why do you want to optimize in the first place? A lot of the things we use just because we've always used them are inherently quite slow. So the idea is to know what you're doing that's inherently slow and try to minimize your reliance on those things. So anytime where you're having to grow memory dynamically, it slows things down a lot because the OS and LabVIEW need to make guesses at how much memory you're going to need. So if you're building an array, bit by bit by bit, LabVIEW says, oh, it looks like you're growing this array. I'm going to allocate you 10 more bytes for your array. And then you fill that up and it says, oh, you've used that up. I'm going to allocate maybe 100 more bytes. So the memory manager underlying LabVIEW is progressively dishing out more memory, but only as needed. And what this results in is a lot of fragmentation of the memory that your program's using. Much better if you know how much memory you need to ask for it all at once and then use that memory, and you'll find that things run blazingly fast. A lot of UI work is slow. Property nodes are generally quite slow in relative terms. 20 years ago, they were really slow. Now everything in LabVIEW is a lot faster, but still, if you're relying on a lot of property nodes in a user interface and it's not snappy, often the reason is because you're trying to tweak properties en masse, in real time. And the last big culprit is disk access. So anytime you're relying on something getting written to the file system, it might work well mostly, but then you'll find that Windows decides to grab some resources once in a while and things slow down periodically. Logging is something that really should be done in a parallel process, if at all possible. So never rely on the logging happening before you can move on to the next part of your code. Little things like that. And when you know some of these things, you'll start to instinctively just use better patterns when you're writing your code. So if you make these practices a habit, then you end up with less problems in the future. Another point is, long ago, I remember having a chat with a guy and he was kind of dissing good software design, saying, oh, don't worry about it. You spend so much time working on your code. It's easier just to buy a faster computer. It's much cheaper and much quicker just to chuck more hardware at the problem and make everything faster. But as many of you know, the pace of development of CPU frequency and the speed at which processors can run is really kind of asymptoting. And we can no longer rely on hardware to fix poor software designs whenever you need to. So there's a bit of an irony with LabVIEW that many people sort of get a sense of at some point. Even though LabVIEW is built around parallel processing and it's almost like the perfect way to do parallel processing, you do parallel code by default with LabVIEW unless you start putting in lots of sequence structures and everything else. But the irony is that a lot of applications are then at the mercy of what is called the UI thread. You can read up on this. There's a link here. I'm sure somehow we'll make this presentation available after. But if you've not come across discussions about the UI thread and root loop, there are certain functions, many of them in LabVIEW, that rely on one particular execution thread to run. And if that thread is doing a lot of stuff, then no matter what you do, you can't make those functions faster because they're all sharing. What you want to do is be able to have things running on multiple threads, multiple cores, because all computers these days are multi-core. So the fact that a lot of things that you want to do, like updating your graph or writing something to disk, are all depending on this one thread, can often be a bottleneck in many applications. So one last piece of data here. This is like a history of processor development, something like that. And the one we're interested in really here is single thread performance. So a lot of metrics go up over time, but you can see here that the single thread performance metric is really flattening out. And what that means is computers these days are not really getting faster when it comes to the performance of one core running one thread. And this is a problem, again, if you're really reliant on a single execution thread, as LabVIEW often is. Okay, so hopefully now you kind of see, well, yes, maybe I do need to speed up my code sometimes. How can I do it? First thing you need to get straight is how to know where the culprits are. How do you find the code that's holding you back? And there are a couple of ways. So the first one is the VI profiler. So this is that dialogue that you might see in the menu sometimes. How many people have used this before? It's kind of, you know, the barrier to entry is not really that high, but it looks a bit menacing sometimes. So basically, it's called performance and memory, something like that. It's built in, which is great. So you don't have to install anything. It's really good when you've got a big project because it'll give you statistical information about every VI that's running. So you can find bottlenecks quite easily just by looking at the mean execution time or the maximum or the minimum execution times of different VIs. And it's great for a first pass. There are problems with its accuracy. There are a whole lot of conditions under which it might report numbers that are not entirely correct. You also don't have great context. So for example, if you've got a piece of code that's being used in 3 places in your application with different inputs and different outputs, you can't tell from the profiler where is the one that's running slow because it doesn't give you that contextual information. It just tells you out of all the times that VI ran, how long did it take? And it's not very good with timing isolation in the sense that you generally have to start the profiler before you start your main application. So if you're trying to profile something that happens halfway through a 3-hour test, it's often very hard to kind of get this testing framework up and running to give meaningful results in just the window that you need them. So it's easy to use though. You just find it in the menus. Timing statistics is the thing you want to turn on. So that gives you the juicy bits. And you just press start before you run your code. You end up with this list of all the VIs in your project. Initially, they all read nothing. At this point, you run your code and wait and wait and wait, let it do its thing. And you can press either the snapshot button or the start button, and you'll start to get some data popping out of this tool. One great thing about this is you can sort things. So in this case, I've sorted by total time. So I want to know out of all the code there, which took the absolute longest. And you can even pop open certain VIs if they've got sub VIs. So this only goes one level deep, but this function read frames to array contains 3 sub VIs, and you can see which of those took the longest. So it's quite good for zeroing in on what was the slowest part of your code. There's a lot more detail about caveats, side effects and things from this kind of tool. Darren Nattinger, who many people know, has a presentation that goes into a lot more detail in the profiler. That's worth checking out. But at some point, you need to drill down a little bit deeper. So the next logical thing to look at is something like a custom timing probe. So a custom timing probe is one of those things that many people have never used or maybe don't really know about or have heard about it, but it sounds a bit tricky. How many times have you had some code and you temporarily throw in a sequence structure, measure the time before, measure the time after, and you know you're not going to keep it there. It's just for the purposes of knowing how long that thing took. Like we do it, right? So how long does it take? At best, a couple of minutes, and then you might forget to delete it at the end, or you think you might need it later, and it's kind of messy. So with a timing probe, what you basically do is you create a custom probe that lets you jump onto any wire, anywhere, and basically measure the difference between 2 or more points in your code. So conceptually, it's very simple, but it tells you a lot about the performance of the thing you're looking at. So how do you do it? It takes a little bit of investment. I'd say literally, 2 minutes if you want to find one in VIPM or somewhere, or maybe to write your own, about 5 minutes maximum. So I'll show you quickly. It's quick and dirty, and it's really not that dirty. Like it's really just quick. There aren't many downsides to a timing probe. They're really good for relative performance. So again, you might not be measuring super accurately exactly the execution of this piece of code because there's a little bit of overhead in doing the probing itself. But if you're looking at, did my changes make the code run faster? It's going to give you a really good indication. And you don't have to add code. So it's a very temporary way to monitor what you're doing. The downsides, okay, it adds a bit of overhead and it can be misleading if you've got things running in parallel. So you've got to use it with, a little bit of sense, a bit of common sense. All you do is right click on a wire, go down to custom probe and grab new. And that's it. That's how you start. You get a little dialog. You can create a new probe. It asks you where you want to save it. By default, it puts it in your user data folder. But exactly the same probe, you can move it into userlib or VIlib. So if you don't like having things under your own name in your LabVIEW installation, or it's a shared PC or something, you can just pop it in userlib or one of the LabVIEW folders, and LabVIEW just finds it. Another thing about this is you can kind of drop a probe in that folder anytime, and whenever you right click that menu, LabVIEW will find it. So it kind of is dynamically checking that folder as you modify it, which is pretty cool. So what you get out is this, and like most NI code, it's zero thought was given to presentation. It's purely about function. So we've got a lot of big, ugly comments and, a blue control that's a long way from the thing it's wired to, but that's okay. It's a simple thing. You need to have a data type. In my case, I right-clicked on an integer, so I get a blue terminal there called X. There's something called Boolean, which is a silly name. That is the thing that you set if you want it to stop execution, pause your code, or break your code. And then the value string is the thing that writes to the probe window the string that you want to display. So it says, do not delete this control. Basically ignore that. The first thing you should do is delete that control. And what that gives you is a probe that's not tied to any particular data type. So normally, if you've ever made custom probes before, if you make an integer probe, you can't use it to probe an error wire or a string or anything else. You can only probe integers. But by deleting that control, you can probe anything. And what does a probe need in order to be a timing probe? It has to have a way to measure the time, to maintain some way of knowing the previous time, so you can get a delta, and some display. You can display the time however you want, and that's it. It's really simple. The only sort of caveat here is probes don't behave like normal VIs. So there's a big long blurb there from the LabVIEW help. The essence of it is if you make a reentrant VI or a non-reentrant VI, it doesn't matter. It treats all probes as non-reentrant, as reentrant. And what you will get is 0 state information stored locally. So shift registers don't work in a custom probe. If you want to store something, you have to find another way to store it, like a global or something. So you can get one on the internet, take 2 minutes. This is on Darren's blog. You can see the interface, the probe watch window. Essentially, you've got a display of delta T there. Do I need the pointer? You can kind of see that. How does this work? Don't know. Probably works. So here, there's a drop down where you can adjust which time you're measuring relative to. So the time difference between the thing you've dropped and some other point in time. To me, that's not ever used really. But anyway, this is simple to use. You can configure the start time and the end time if you want. And it's got an explicit display of what you need. The downside is this probe, even though Darren's a great guy and produces good things, it contains 1, 2, 3, 4, 5, like 11 things inside an LLB to make this probe work, including an X control. I don't know. I don't know why you need all that stuff. So my favorite timing probe, you basically just pull it down. I've called mine delta T. What you get is the time since the previous instance of any other one of your delta T probes. So it will give you the difference between the probe you just dropped and the last one that ran. If you only drop one probe and you have it in a loop, it'll just give you the time since the last iteration of the loop. And in my mind, it solves 99.9% of your timing probe needs. Also, the code looks like that. It's just a single VI, a single element queue to keep the time because you can reference that across different VIs, and some formatting. And that's it. So single VI is neat, 0 configuration. You can use 1 or more instances. The downside, there's 0 configuration. So if you need to do complicated timing to measure relative times between 10 arbitrary things in your code, you need like a better version. Okay. The last thing you need to do, once you've found your VI that's slow or your part of code that you want to optimize, sometimes you need to dig a bit deeper and find more accurate ways to profile what's going on. So this is where you start dropping down high resolution timers and the like. Now, you don't need to do this often, but when you do need to do it, you need to do it properly. So the best thing to do first is to isolate the code you're trying to profile, which means put it into a sub VI or something. Don't try and profile things in a sea of wires in your spaghetti application. You'll get misleading results. You have to use the high resolution timer because, well, you want to use the most accurate timer you've got. The millisecond timer, we way surpassed millisecond timing accuracy, like, more than 10 years ago. So timing should be accurate. Often you have things that run so fast that you can't just time them directly. So if you try to profile how long the add primitive takes, it's going to be nanoseconds. So you can't use a millisecond or microsecond timer to time that thing. So you often have to loop. You can put an array through, like of 1 million elements, time how long it takes to add all those things 1 million times, and then divide the result by 1 million, something like that. The last thing, which is something that many people don't intuitively realize, repeat your test a number of times and always take the lowest result. You don't take the average time or the maximum, the worst case. So the logic here is that your timing is going to be really, really good unless something else gets in the way, like Windows decides to do an update, or someone is interacting with some other program, or something else is consuming resources. So those conditions are like not normal, but your base performance, if you measure something as taking 3.2 milliseconds, then it can, you have like a lower bound on the time. And if you measure it the next day and it runs at 3.1, you know that it can possibly run even faster than 3.2, right? But you don't know what the upper limit is. It could be anything, depending on what's going on. So for profiling, you want to always take the lowest number. There's a few other considerations which are really important to get good results. You have to disable debugging. Don't do things like updating front panel indicators in a loop unless you are trying to profile how long that takes. You've got to be really careful with the inputs you provide to your test harness. So you can't use constants on the diagram generally, because LabVIEW tries to optimize things out. It says, oh, hey, I know exactly the data going in here, so I'm going to cache the inputs, and you don't get meaningful results. And it's good to wire up all the outputs that you can, because again, the compiler is kind of clever and it says, oh, you didn't wire any of those outputs, I'm not going to calculate them. And I might show in one of the demos, there are functions that change in performance time depending on which outputs you wire, primitives, yellow primitives. So LabVIEW is a bit clever about knowing which parts it needs to calculate and which it can skip on. So when you're profiling, you have to wire up what you need and wire them outside of the test harness. Inlining is a question that often comes up. Should I inline things to make them faster? I would say no. So you're better off doing all your profiling without inlining, because you'll get consistent, meaningful results. And inlining will always, well, for simple code, inlining will always give you some improvement. So that's the kind of thing that is quite hard to work with at the time. You can't easily probe inline code and things like that, but you can kind of know that inlining is like a little bit of extra speed that you carry around in your pocket if you need it. But for the purposes of benchmarking and profiling, it's not sort of necessary. All right, so simple way to profile the case structure. I like to use stacked sequence structures when I do it, because you don't need to see the first frame. You want to see the middle frame, which is some code under test, and you don't really care about seeing the last frame, where I'm just calculating a delta. So space-wise, I find this more efficient. Now, as I said before, if the code you're measuring is really fast anyway, and you just want to make it twice as fast, you often have to use an array at the input or something like that. So you can see here that I've got an array with some number of iterations to build some random numbers. And then at the output, I'm dividing by the size of that array. So I get effectively the average time per iteration to give me a time. And the last thing you can do is add like another loop around the whole thing to repeat the test. So you want to repeat the test a bunch of times. Definitely the first time will always be the slowest. There's a whole lot of resource jiggling that happens. And you can pretty much see in every case, the first time you run some code, it'll be slower. And the second, third, fourth time will be much faster. So run at least twice, 10 times is good, and take the lowest result. Okay, so let's do a little demo. got a little sample application here, which is displaying an image. What's a color? Can someone give me a color? Orange is already there. There's green. So let's speed this up. So it's a looping graphic, just drawing something. I'm drawing some code in a picked control and doing some filtering at the same time, just so I've got something to profile. So what you can do, if you want to use the performance tool to monitor this, you have to stop the code first, go in here, turn on the timing statistics, then start the monitoring, then run your code, and then you can take a snapshot here or there. You can keep the performance tool running and take snapshots whenever you want. In this case, I don't care. It's just doing the same thing in a loop. One snapshot's good enough. So I can see that filter image is taking a long time, on average 55 milliseconds. That's the slowest thing that I'm running. Then another one here, read frames array, that's taking 32 seconds. This one happens to have some sub VIs. So there's the things that are taking the longest in here. So filter image, if I go into my code, what I could do is drop a timing probe in here, custom probe delta T. I can put one before and after. And I can see in my timing probe, it's like 56 milliseconds. So the number is consistent. In this case, I would use the performance tool to find where's the slow code. Then you can go in and kind of verify that the performance is like about what the timing tool, the performance tool says, and use your custom timing probe or something to get more detailed information. So that's all cool. If I make the filter like, you know, broader, wider, then you can see the graph at the bottom, everything gets slower. So you can build tests to provide a range of data for you to profile. And that is often a good way to do your testing. So profiling is kind of easy, but quite important. You have to do a good job with your profiling before you move on to optimization. So here we're basically going to do a bunch of demos, but first a little bit of an intro. What are the main things that are worth looking at when you're trying to make things faster? So some functions are just really efficient and some are not. So try to use constructs that lend themselves to efficiency. Parallel for loops were introduced a while ago, and when you can use them, they give you a boost almost always. So if you can't use them, there are some reasons that you can't use them, too bad, but whenever you can use them, on pretty much any PC, you always see performance get better. There are a few kind of caveats there. If you've got nested loops, you should only turn on parallelized parallelism on the outer one of your nested loops. So don't just go around blindly making all your for loops parallel. You have to know a little bit about what you're doing, but not too much. There are also a lot of built-in functions where there might be multiple ways to do the same thing, and one way is fast and one way is slow. So often the functions differ a little bit in their capabilities, but for certain applications, you can use either function. You should always use the fast one, right? That's just good to know. Second thing is pre-allocate memory whenever you can. So if you're doing any work with large arrays, it's really good to pre-allocate when you know how big the array needs to be. Often we use lots of loops for signal processing and any kind of data analysis. You're looping through lots of data. Anytime you want to speed stuff up, it's normally because you've got lots of data. So it's really good to look at whether you can get rid of loops. Like sometimes you see this kind of sequential code where people have a loop where they're building something, then a loop where they go through processing things, and a loop where they go through and display stuff. Where what you can often do is chain all those inner steps together inside one loop and do the whole lot kind of within one construct. That's always good to do. And watch out for resource contention. So we spoke before about certain UI updates, disk access. The last thing, which is probably the most noteworthy, out of any speed grab that you can get, the thing that always gives you the biggest boost, for sure, every single time, is using lookup tables. So anytime that you can pre-calculate something and then look up with that pre-calculated data, you'll get speed boosts of like 10 times or, orders of magnitude boost. A lot of the things you might find that one function compared to another is like 20% faster, but like 10 times faster is like 1,000%. It's orders of magnitude more than many of the other things. So lookups are probably the most underused way of speeding things up. Okay, let's do some more demos. So what I'm doing for my demos here, they're all kind of the same. I've got some profiling code wrapped around an inner case structure. And what my little test framework is doing here is just going through different ways of performing certain tasks and displaying the time for each one. So the reason I've got so many loops, one of the loops is looping through all the internal cases, so profiling each different test, and the other is repeating the test many times. So, well, I'll keep that open. Let's run a little bit here. So, just going to loop this. Simple arithmetic. I've got a whole bunch of inputs and I'm doing some numeric operations on a whole lot of data, just primitives. So this is our baseline. This is a good one, by the way. See what happens when I drag this window around? Do you see how the graph redraw stops? UI thread. So when you interact with a Windows window, suddenly LabVIEW says, oh, I can't get resources to draw my graph anymore. This is why you got to watch out for, UI thread. In any case, compound arithmetic, do you think it's going to be faster or slower? I'll show you the code. The same operations, but done in one node. What are they doing in there? Don't all guess at once. It's quite a bit faster. Yeah, well, you saw the answer, so that doesn't count. You're not getting a mechanical pencil. So let's have a look at a few more. Formula node. Do you think formula nodes are fast or slow? Faster. They're slower. They're slower, but I seem to remember from many years ago that they were really slow. They did, right? Yeah. So anyone with grey hair in the room, you can ask them about formula nodes. They used to be really slow, but in this case, they're not that much slower. ExpressVI. Same as formula node, basically. Who would have thought? So let's, here's the point. I'm doing the same code, basically. The ExpressVI is the same code, just with a lot of inputs. The next thing is something that I was just mucking around with, parallel arithmetic. So on other machines that I tested this on, what is parallel arithmetic? Okay, this is when instead of just chaining a bunch of arithmetic operations together, you do them in parallel where you can first. So on two other machines I tried this on, which were desktops, mind you, this was much faster than all the others. And when you stop and think about it, okay, LabVIEW can do things in parallel, right? So if you do the pre-multiplications in parallel, 4 in a row, 4 in parallel, and then fan that down to the next and the next layer, you can see why that could be faster. So in this case, it performs about the same as the compound arithmetic. But yeah, same deal with the last one, parallel formula node. So where did that go? I'll compare that to the other formula node. Parallel formula node is much faster than the normal formula node. So the parallel one, even though you're scripting all these things in sequence, I presume there's some optimization that happens under the hood that says, hey, I can pre-calculate some of these at the same time. So definitely the parallel thing, even though it's not so apparent with this operation for the primitives, it ran faster on other machines. So it's a good example of why you should test on multiple machines, if nothing else. Okay, building arrays. Building arrays like different ways. So in this case, I'm adding random numbers to an array inside a for loop. Okay, this is our baseline. So 1,000 samples, like depending on the computer you're on, you can make this slow by giving it more samples, but I'm just going to stick with a number that's kind of snappy. So if I build from the other end, like add the elements to the front of the array, look what happens. So try and manage my code a bit better here. This is nothing amazing. I'm just adding to the other end of the array. And suddenly the performance is, instead of 55 nanoseconds, it's like 140. That's like way worse. So try and build arrays the right way if you have a choice, if you're working with large amounts of data. Next one, what if I get tricky? What if I reverse the array first, then add it to the end, and then reverse the array at the end? Because you all know that reversing an array is basically a no-op in LabVIEW, right? So LabVIEW is very smart. It knows that it can index backwards through an array if you just put a reverse array on the diagram. However, in this case, it's a lot slower. It's a no-op if you're doing something like indexing and reading out the data and not modifying things. But in this case, because we're growing the memory requirement of that chunk of memory, LabVIEW, it can do the pointer magic and reverse the array for free. But when it has to add an element, it freaks out and says, oh, I'm going to have to allocate more memory for that every time. And you get like a massive speed hit. Last couple here, pre-allocate the array and then replace the elements one by one. It's much faster, right? So compared to the normal build array with shift registers, this is like 12 nanoseconds as opposed to 55. So 4 times faster than the shift register version. And the last one, which is a few LabVIEW versions old, is just auto indexing the output. So don't try and do anything fancy. And this is on par with the pre-allocate. So I'll turn some of these off. It's in fact a little bit faster than pre-allocating. Again, on other machines, you might find this is even faster, but LabVIEW's memory manager is quite good at auto-indexing tunnels for some reason. So it's one of the few examples where pre-allocating doesn't win by a mile. Okay, I'm going to fly through. Building strings. So what am I doing here? This was a funny one. So all I'm doing is adding some pre-pending and post-pending, some strings. Where's my mouse gone? Okay, let's run. So if I build the string just adding a string before, instead of before and after, it's a little bit faster, which is kind of good. If I just add a string at the end, it's even faster. So this is a bit like arrays. If you try and add stuff at the beginning, it's harder for the compiler than adding stuff at the end. And that works with strings because, believe it or not, strings are like arrays. Now, something that I've done quite a lot, bit of a confession, I like this kind of format where you kind of structure your text, even if I'm not using like the numeric formatting syntax of formatting a number to 3 decimal places with hide trailing zeros or something. I kind of like the cleanness of this representation, prefix, then a string, then a suffix. Unfortunately, doing that compared to basic formatting is like way slower. So the poor man just build string is a lot faster than trying to be fancy with your formatting. even though you're not doing any actual calculation. And the same goes with the same kind of construct if you format adding something, should show you the code, you're adding a prefix just at the beginning or adding a suffix just at the end. They're also a little bit faster because you're adding less stuff, but still way slower than just standard string build. Okay. Match pattern. This is a very well-used VI. I'm sure you all know what it is. So match pattern has two uses, really. One is when you've got some kind of wild card or some expression that you're trying to use. It could be like you're matching a range of different letters or something. If you're doing any kind of parsing, you often need to do complex matches. But the kind we're going to focus on here is when you've got a fixed string and you're trying to find that in some body of text. So I've got a little random number generator in this code, and I'm inserting a token called token somewhere in that random string, and then I'm trying to find it. So if I run this, just looking for this little needle in my haystack, I'm sitting at around, what, 180 nanoseconds per operation. You can do the same thing using the split string function, which is sort of hidden away in the advanced string functions, and most people don't really use this much. So what it does is instead of doing all the kind of wildcard, regular expression-y stuff, it just searches for a fixed string inside a string. And this is what, 50% faster or something than the match pattern. So when you don't need to do all the matching gymnastics, using this just to find a known constant thing is a much better way to do things. Same sort of thing. This has got multiple outputs. So you might be looking at the thing before the token, or you might be trying to find the thing after the token, and the performance is different. So if I grab what's after the match, it's a little bit slower than the regular before the match. And same with search and split. If I grab, so the green one is looking what's after the match compared to what's before. So OpenG has a function to do this. So let's go with matching things after. The OpenG toolkit is great, but in this case, the OpenG version, which attempts to be really efficient by instead of doing the fully blown match using match pattern, let's have a look inside. It basically uses search string and then indexes the bit out at the end after the match. And this should be fast, but you can see here it's slower than the other two options, either using the raw match pattern or the raw search string. But if you inline it, suddenly it becomes way faster. So an interesting point to make here, I've got two bits of code down here. This one is basically the code running inside the OpenG function, just dropped on the diagram, and it's taking 220 nanoseconds or something. Putting that inside a VI and inlining it is actually faster than dropping the raw code on your diagram. And this is not something that people sort of register. It's faster to have the code wrapped up in a sub-VI and inlined. You would think there's some overhead that happens somewhere, but it turns out to be faster. So it's kind of a good reason why you should package up functions you use a lot in sub-VIs and use them like that. And inlining is good. All right. Okay. So strings are byte arrays, right? They're quite interchangeable. This is an interesting demo. Let's run it. So in this case, I'm picking out a certain part of a string using string subset. So I'm pulling out a random length of characters from some position into the string. And I can do the same using array functions. There's an array subset function. That is slower, right? So working with an array in this case is slower. The same thing you can do with a replace. So I can replace a substring, and that's somewhere else. I'll turn the original ones off. If I use the array function to do the replace, it's faster. So my code here is converting the strings to byte arrays and using an array function to replace and then converting back. And even with all the conversion, which is probably just a reinterpretation of the bytes, the array version is faster. So, you know, who would know? If you ever need that, you can credit me appropriately. Trim white space. So this is another good one. Any kind of parsing, if you're doing some roll your own XML parsing or JSON or this or that, like reading a CSV file, we're often trimming white space from strings. So the built-in LabVIEW version is, you know, looks okay, right? Until you think, well, what about the OpenG version? Those guys are smart, they've thought about it. This is faster. So 280 nanoseconds versus about 200 nanoseconds. That's good. They make it faster by using lookup tables. So what they do is take every possible white space character and build it into an array, because ASCII characters are like a byte. So you need to populate a table of at most 256 elements and then just look up in that table whether this is a white space or not. So they're using that to find the start and the end of the white space and then pulling out the string that they need. That's the shipping OpenG version, and it's faster. If you inline it, it goes down to less than half of the original function, which is great. And with a little bit more optimization, you can bring that down just a fraction more. There's also a bug in the OpenG version. It doesn't work with removing leading space if your string that you're searching is all space. But, you know, no one's obviously complained about that. The really fast one doesn't have that bug and does a better job. So 2 more. Can we squeeze in 2 more? Do 2 more. All right. This is a slow one. Okay. So this is comparing different ways of rendering images. So what you're seeing here, I took a GIF from the internet, a looping GIF with about 50 frames or something, and I pulled apart the image into multiple frames, and I'm using those frames as an array that I chuck in, and then my inner loop that I'm benchmarking here is displaying that array in a few different ways. The first one is using a graph control, an intensity graph. So if you make an intensity graph the size of the image you're trying to display, you can see here this image on the left looks like it's doing nothing. The reason it looks like it's doing nothing, I need to add some delay. Now you can see a bit more clearly what's happening. So I have to insert delay to allow you to see the updates on some of these. The intensity graph is so fast that it's basically instantaneous. So if you need to display an image as fast as humanly possible, then displaying the pixels in an intensity graph is by far the fastest way to do it. The second one is a pict control. And to display data in a pict control, you have to use this kind of janky format thing. This is a bit ugly because it does some pre-formatting of the data into some proprietary type, which is derived from the way Apple Macintoshes store their bytes from the early days of LabVIEW. And then, and then after that, it's doing the kind of rendering section. Somewhere. Okay, this is the rendering part. Basically, what it's doing is just building a string which it casts as a pict control. So I just made an optimized version of that, which is, I'll skip to the last one, picked control optimized. This is the bits you actually need of that code. This, the kind of most verbose part at the front is just calculating the bounds for the region of interest thing. And then you're just literally formatting a string as some sort of random byte array and chucking it all into a picked control. So the optimized version here, let's see, I'm going to reset this for now. Okay, so the intensity graph is way faster. I'm going to turn that off. The third one is an IMAC control. So the IMAC control is, I'm cheating a little bit in that what I'm doing is I'm building the image outside of my loop and then just displaying inside and then deleting the image outside of my loop, which is fine. That's what you would normally do in an application. So the IMAC control is running about the same speed as the optimized picked control, which is cool. There is one more point on this though. So I'm going to stop this. What I'm doing here is I'm updating each of these controls using their actual terminal. So I'm writing to the intensity graph as a terminal. The same with the picked control. I'm writing directly into the picked control. I've got another frame here. So this is the same code, but now I'm using a reference and updating using a value property. And the reason I've included this is because this is generally more likely how you would have to write your code when you're doing some kind of display in a sub VI or something and having to render it to a front panel. You don't always have the luxury of having the actual control terminal at your disposal. And the reason this is interesting is suddenly everything gets a lot slower. So I'm just going to reset my graphs here. The intensity graph is now much slower. It's the first one, the red one. The IMAC control is much, much faster. And the picked control and the optimized picked control are almost indistinguishable. So most of the overhead in rendering a picked control is writing to the actual terminal rather than the calculation of the frames, which is kind of interesting. And by contrast, the IMAC control, it's a sort of a reference-based world. So whether you're writing to the value property or the terminal itself, under the hood, it's kind of the same. And LabVIEW writes your IMAC control at a similar sort of speed to the original IMAC update. So the reason I'm mentioning IMAC controls is not to alienate 3/4 of the room. IMAC controls are not expensive. They're actually free. So you can use the IMAC display for free by downloading IMAC and just not installing IMAC DX and IMAC IO. And you can drop your mouse again. So you can deploy the IMAC control with all its region of interest stuff and overlays and all the functionality that's there without paying any deployments or any licensing, which is kind of cool. If you need a really performant application displaying stuff, then IMAC is probably the king. Very last one before I'm done. This is like a little bit more complex example. I wanted to demonstrate the lookup in kind of a real world scenario. So let's run it quickly. Here's a 16-bit image, so 65,000 possible values. And here's like I guess like a heat map or something where you can dynamically alter this stuff. So what I'm doing in the code is I'm building a color map and then applying that color map to every pixel in the image. There's 1 million pixels in this image. So the naive way to do this is to loop through the arrays or through your image and do like a pixel interpolation for each of the R, G, and B channels to build your output. And there aren't really alternatives, any faster alternatives to this in terms of the interpolation. So you're kind of stuck with doing this amount of work to calculate your pixel values. But what you can do So there's 1 million pixels in the image, but in the color map, there's only 65,000 possible values that you could ever need to update. So what I'm doing here instead is pre-building the lookup table by making a 65,000 element array of all possible color values, color mappings. And then to apply that, all I have to do is index into an array. So you go through your image and just look up for every pixel. And this is the one that's going to run 1 million times. And look at the timing here. 21 milliseconds to use the lookup table, 269 milliseconds to do it pixel by pixel. So even though you have to go through the overhead of building this quite large lookup table, you know, it's going to take up quite a bit of memory, it's way faster than going through every pixel of your data and updating as you go.